Feel free to ask me any questions if you have them. I see Bruce is still trying to log in. We got about 3 minutes before class starts. All right, got another person coming in. All right, so I only have 5 of you guys. I'm supposed to have more than that in the class, but anyways, it is time to start. Mariana's asked a question. Yes, Mariana. She says for the test on Thursday, we're only allowed to have the formula sheet, right? So you are allowed to have the formula sheet. If you look on our Canvas page, there's something called allowed equations. That's got some kind of name like that in it. That's the actual equation sheet you're allowed. You can print that out and bring it yourself. It should also be down at the bottom of the test, where you also find the inside cover of the physical textbook, the inside front cover and inside back cover. That has a lot of prefixes and special constants and stuff like that. That will be there as well as a periodic table. But other than that, you are allowed to bring a scientific slash graphing calculator, either one of those. It just can't be a scientific slash graphing calculator that's on your iPad or on your iPhone or on your phone or on your tablet of some sort. It can't be on something that accesses the internet. And during the actual face-to-face test, you will need your lockdown browser. I sent out an email about that this morning, so make sure you have that. As far as scratch paper goes, I usually have several sheets in my classroom when I'm doing it. Perhaps Mr. Askovic might do the same thing, but you're allowed to have blank paper in addition to the actual equation sheet, but it's got to be blank, and you're not allowed to add any other stuff to the allowed equation sheets. Anyone else have any questions? All right. Well, when we last met, we finished doing some calorimetry problems. For instance, we calculated what would be the specific heat of copper, and I just made up some random numbers and actually came pretty close. It was like 0.083, and I think the actual specific heat of copper is 0.093 or 0.091 or something like that. So it was actually pretty close, not too bad. But that's a realistic problem. That's in fact exactly the same problem you'll do in probably one of your labs. I think Mr. Askovic is also planning on doing a lab where we do the specific heat. So you'll get to do a very similar calculation to that. And I started talking, even though I'd already talked a little bit about it, I started talking about latent heat. So there's a latent heat of fusion, and there's a latent heat of vaporization, and then does anybody know what happens when CO2 melts? So, for instance, you can have CO2 as a solid, and when that melts, do y'all know what happens there in most circumstances? Okay, so yes, it sublimates. Good job, Ethan. So yeah, it sublimates. Dry ice is CO2. It's frozen CO2. So if you actually have dry ice, the reason why it's called dry ice is it goes straight from the solid state to the gaseous state and doesn't go through the liquid state. So in addition to the latent heat of fusion and the latent heat of vaporization, there also exists a latent heat of sublimation. They might call it something different, but as far as I know, it's latent heat of sublimation. But what it means is basically the latent heat of fusion is sort of the remaining potential energy that keeps the molecules in the lattice attracted to one another. So you have a molecule here, and then an identical molecule here, and another molecule here, and then below that's another row, and it's obviously way more than three molecules, and obviously way more than two rows of molecules as well. But then there's another layer of molecules just like that back behind it, and another one still. So you've got this lattice of molecules, and the heat of fusion is sort of the energy that it takes to break those bonds between those adjacent molecules. So, in addition to bringing, for instance, water up to 0 degrees Celsius so that it can melt, water ice that is, up to 0 degrees Celsius so that it can melt, you also have to add some more heat called the latent heat of fusion, and that's an added heat. That has to be added to break those bonds. When that happens, that breaks the lattice bonds, and then the individual molecules, which were maybe this far apart, now are a little bit further apart. And instead of like you have in the lattice where you've got this molecule and this molecule, and they're pretty much always right next to each other, in the actual liquid state, you have this molecule and this molecule, and they sort of roll over each other. Maybe that lasts for a microsecond or a nanosecond. I really don't know the order of magnitude. So I'm literally saying micro or nano because I don't know how long it is. But the main thing is these two molecules will stay next to each other for a very short period of time. And then one of those molecules will go off and do the same thing with another molecule. And the other molecule will go off with yet another molecule and do the same thing. And by rolling around on top of each other, that's how it behaves characteristically as a liquid as opposed to a solid. But as you can tell, since this molecule is sort of rolling on that molecule, there's still some energy of attraction that's pulling those molecules somewhat together. So after you add heat to bring that water that's now liquid water from 0 degrees Celsius up to 100 degrees Celsius, assuming 1 atmosphere pressure, that's going to bring it all to basically a point where it's ready to boil. And in fact, all the water will stay at 100 degrees Celsius, just like when you were going from freezing to liquid, all the water stayed at 0 degrees Celsius until every bit of the water became liquid. At that point, then the temperature could change. And the temperature changed all the way up to 100, and then it locked down at 100 until every bit of the water actually boils away. Now, in order for that boiling away to happen, it has to reach that 100 degrees. So that's going to take a good amount of energy to bring the water up from 0 degrees to 100 degrees. But then there's going to take a latent heat of vaporization to be added. And that heat is the equivalent of the amount of energy it takes to break those still molecular bonds between adjacent molecules. Again, not the full strength that the lattice had in the solid state, but still some affinity for one another is there, and therefore experimentally you can determine what that latent heat of vaporization is. And again, that's a heat added to the actual liquid to make it jump into the actual gaseous state. Okay, so that's what your latent heats are. Uh, what I have discovered over time is it gets sometimes kind of confusing when you're trying to solve calorimetry problems that involve changes of state, because it's really sometimes you get a little confused. You don't know whether the heat of fusion should be a positive or negative quantity depending on which direction you're going. So instead of that, I always just say Q lost equals Q gained, as opposed to the sum of all the Q's equals 0. Okay. So that's the re-intro to latent heats. And now I'm going to solve an actual problem with it so you can see how it works. And I'm using a table that's table 19.2 on in your textbook. So I'll just say it's table 19.2. Obviously, when you're in an electronic textbook, it's hard to tell what the actual pages are. So let me start by sharing my screen with you. Oh yeah, by the way, does anyone have any other questions regarding homework before we get started on this? Again, I always offer the first 5 to 10 minutes where you can ask me questions about past homework. You can also, of course, save it to the end. But if you have any questions and I forget to ask if you have any, by all means, interrupt me and ask. So does anybody have any questions about past homeworks, or like Mariana asked about a test, for instance, or about the syllabus or anything?
There was something in the homework called like physics primer.
Mhm.
What is that?
That is basically one showing you some of the basics of physics, but mainly as it compares to how you're going to do physics in the mastering physics program. So it does things like shows you how to put graphs. For instance, some of the problems will have graphs on it, and you'll have to put little dots, and some of them have vectors, and you have to stretch them out. So the physics primer and the intro to mastering, those two things I normally count them as extra credit, and that's why they're counting here as well. But they do teach you how to properly use MyLab and mastering, so I highly recommend that you do them, and they do count as extra credit. And you'll notice I didn't put like the first week as being due. So, anyways, any other questions? All right. Well, we had an extra person come in, and then it dropped back down. So I don't know what happened to the other person. He fell down. Okay. All right. So I'm going to share my screen with my iPhone/iPad, which is actually my iPad. You know, when Steve Jobs introduced the iPad, I remember watching that day, and the reporters were like, "Didn't he even, talk to at least one female about this idea?" And everybody laughed, and guess what? He was right. He just steamrolled them, and it worked fine. Everybody loves the iPad now. So, anyways, I just remembered that, and it cracked me up that everybody thought, yeah, this name's got to change because that's just the stupidest name ever. But anyways, here we go. Example one: how much energy must be removed from 10.0 kilograms of water at 20.0 degrees Celsius if we wish it to turn into 10 grams of ice at negative 15.0 degrees Celsius? So that's the actual problem we're asked. I think that's pretty straightforward. What I'm going to say is solution, and I'm going to make actually, I'm going to go ahead and write down the equations that I will need for this and the data that I'll need. So we know that the heat added to a mass M of substance with specific heat C is given by MC times delta T. And we know that delta T in general is T final minus T initial. Of course, we also know that when I use uh, Q loss equals Q gain, I don't stick to that convention. I just have to make sure that all the terms are positive. Okay. So keep that in mind. And then there's also a certain amount of heat Q that you have to supply to a mass M whose latent heat is L, and that heat is given by M times L. Okay, so that's what it needs to actually change state. In this case, we have the mass of the ice, which equals the mass of the water, which equals just the mass, and that is 10.0 kilograms. Okay. What I also know is that the specific heat of water, so C of H2O solid, which is ice, is 0.50 calories per gram Celsius degree. And I know that the specific heat of water in the liquid state is 1.00 calories per gram Celsius degree. Now, if you look at your book, you'll see that that's specifically for water at 15 degrees Celsius, which is halfway between the 14.5 and the 15.5 that I told you was part of the definition of the calorie. So, in principle, if you're going a whole range of temperatures beyond 15, then you need to look up the most close values of specific heat to the temperature that you're dealing with. But we're going to pretend like it's basically one all the way, and that'll be fine. Okay. We're going to pretend like the specific heat of ice is going to be 0.50, and that also is for a very specific temperature, but we're going to pretend like that works for all the above. Now, I'm also going to show you that the latent heat of fusion, which is, remember, fusion is the one where we're basically going from a liquid to a solid. And then vaporization is when we're going from a liquid to a gas. So the heat of fusion is what we need. And I'm going to write latent heat of fusion for H2O. And again, I'm looking at table 19.2, and it says the heat of fusion for water is 79.7, and that's calories per gram, which also is calories per kilocalories per kilogram. That's acceptable as well. And I'm just going to write right here table 19. I'll say tables 19.1 and 19.2. The 19.1 is the table for specific heats. Oh, okay. Was that? Who was? Oh, okay, gotcha. Sorry about that, everybody. All right, so yeah, 19.1 is where I get the specific heats, and 19.2 is where I get the heat of fusion, heat of vaporization. You also know that 19.2 comes with the melting points and boiling points, which is critical, but you already know what it is for water. Okay. So what I'm going to say is the total heat required to do what we're asking is going to be MC delta T, where we're going to have to actually take heat away because we're actually removing heat from water. So we should get a negative amount of heat that we're pulling out of it to decrease the temperature. Okay. We're going to have to decrease the temperature, in fact, from 20 degrees Celsius down to 0 degrees Celsius. So that's a fixed thing. And then we're going to have to change the state. So that's going to be the mass times the latent heat of fusion, in this case, of H2O. And this would be H2O for the liquid state. Now, after we bring it down to that temperature of 0 degrees Celsius, and then we apply enough heat for the latent heat of fusion, then we have to bring the temperature further down because we want the final temperature to be negative 15 degrees Celsius. So I'm going to put another term there, and that's going to be the mass, which is the 10 kilograms, of course, times specific heat of water. But in this case, it's going to be of solid water. So that's ice. So I'll put it with a subscript S on it. And then this case is going to be, again, delta T. Okay. Now, in this case, I'm just asked to calculate the total heat removed in order to convert the 10 kilograms of water at 20 degrees Celsius to 10 kilograms of ice at negative 15 degrees Celsius. So all of these heat should be negative, and therefore we're going to just blindly make this latent heat of fusion negative, and we'll just make sure the final temperature, obviously being less than the initial temperature, is going to make all those negative. So just to keep in track of all that, that's how it's going to work out. So I'm going to write down 10.0 kilograms. Now, you don't necessarily have to write these units every time, but you should every time think about what the units are to make sure that they're working properly. Uh, I'm writing them down at least for this first pass. Now, the specific heat of water is 1.00 calories per gram Celsius degree. Uh, but I could also say that's kilocalories per kilogram. So that's what I'm going to do, kilocalories per kilogram. And then the final temperature is going to be 0.0 degrees Celsius minus the initial temperature, which is 20.0 degrees Celsius. And then plus, actually, since the M is common to all of them, I'm going to go ahead and factor out the M and put square brackets around it. So I only have to include that mass that one time out there. Now I'm going to say the latent heat of fusion. I'm going to force this to be negative because I know I have to take heat out. So I'm going to write negative 79.7 kilocalories per kilogram. And that takes care of the heat of fusion term. And notice I did put the sign in. And then finally, I need the change of temperature term for the solid water, which would be ice, of course. And we've already got the 10 kilograms out front, so I don't really have to do anything with that. But I do have to write down that it's 0.50 kilocalories per kilogram Celsius degree. And now I'm bringing it to negative 15.0 minus 0. Sorry for running out of room there. Hopefully y'all can still see that. It's negative 15.0 minus 0. So this is going to be 10.0 kilograms, and my dog's going to help me out by just barking at random times, so that should be wonderful. If I take 1 kilogram and multiply it by 0, obviously that's going to give me 0, so I don't have to do anything with that. But if I take the one, I don't know why I said kilogram. If I take 1 kilocalorie per kilogram Celsius degree and multiply that by negative 20, then I'm going to get negative 20.0. And notice the Celsius degrees cancel out by the subtraction. So I end up getting kcals per kilogram. Okay, so that's the first number. Actually, that's sort of the second number because the 0 already gave me a 0. Now I'll say minus 79.7 kilocalories per kilogram. And then finally, 0.5 times negative 15 is going to give me negative 7.5. So that's negative 7.5 kilocalories per kilogram. And then the 0.5 times 0 is going to give me 0. So really what I'm showing here is there is a plus 0 there, and there's a plus 0 there as well. And I'm leaving those out because they're 0. There's really no point in it. Okay. So now I'm going to go ahead, and you can see that the kilogram is going to cancel out with the kilogram. Oops. It's going to cancel out with the kilograms in the bottom. So this kilogram is going to cancel out with that one, and that one. So ultimately, we're going to get a result in kilocalories. And what I can see is I'm going to have negative 20 minus 79.7 minus 7.5. And that gives me negative 107.2. And then I got to multiply that by 10. So, and you don't even need your calculator for that, hopefully, which is 1072. So it's going to be negative, it's going to be negative 1072 kilocalories. And that should be the total amount of energy that has to be removed to convert it all to ice. Now, you could also do that in kilojoules or in joules. That would all be fine. What I want to think about here is when I add these numbers, I actually get 107.2 to 1 decimal place. So that gave me 3 sig figs, and then I multiplied 3 sig figs times 3 sig figs. That gave me, of course, 3 sig figs. So that means this digit right here is not a significant figure. So really just to keep track of sig figs, it should be called negative 1.072 times 10 to the third kilocalories. And then of course I can say that 4.186 kilojoule, oops, I don't want to put it down there, sorry. I can say that 1.00 kilocalories is equal to 4.186 kilojoules. And therefore, my answer would be basically negative 4.487, negative 4.48. And I'll keep one extra sig fig or one extra digit. That's going to be a non sig fig. And that's times 10 to the third. And that answer is in kilojoules. Okay. So both of these are answers. Anybody have any questions with that? Anybody have any questions on that one? I don't know why I said the word with there. Does that make sense to everyone? I'm going to make sure you guys can chat with me. I forgot to put that out there. Okay, got it now. So there's still no questions. That all seems pretty reasonable to you guys. So, for instance, if you were to actually take 10 kilograms of water, maybe, in a big plastic, tote or something like that, and stuck it in a freezer, what you're saying is that that freezer is going to have to remove about 4.487 million joules from that water to actually turn it into water at negative 15 degrees, or excuse me, to turn it into water ice at negative 15.0 degrees Celsius. Now, the way that would do it is basically you'll have to set up a system where you can send let's say, a working substance like Freon, which is what we used to use, or something along those lines. You'd send that through in such a way that it was actually a little bit warmer, and then it being well, actually, for it being a little colder, the Freon at low pressure, or whatever chemical you end up using at low pressure, would be quite a low temperature. And therefore, it would take any of the air or anything it comes in contact to, say that little metal pipe comes in contact to, that would actually steal heat from that air or the other things it's in contact with. And then it would heat up the working substance. The working substance would then go back through the compressor. The compressor could basically go through the process of increasing the temperature, letting out the heat, decreasing the temperature again, sending it back through, and slowly over time you can pull out enough heat that way that it ultimately would freeze. And that's how refrigerators work, essentially, refrigerators and freezers. Anybody have any questions on that? All right, so let's look at another example. This is example 2. It says, in an attempt to make iced tea, I don't know if you know this, but when we say iced tea, what we mean by that is tea that may or may not have ice in it. Ideally, it should have a little bit of ice, but the main thing is it had enough ice in it that the tea itself was at 0 degrees Celsius. Okay, that's the ideal scenario. So we want the tea, and the ice to basically form in such a way that ultimately the tea that you're drinking has a temperature of 0.0 degrees Celsius, and maybe even you still have some ice floating around in it, because some people just actually like the ice. So that's what we're going to do here. It says, in an attempt to make iced tea, a 1.00 kilogram chunk of ice at negative 15 degrees Celsius is placed in a 5.00 kilograms of tea at 20.0 degrees Celsius. and I say fully describe the equilibrium. I ran out of room there. Actually, I didn't have to. Let me go ahead and write that just for the heck of it. So I'm going to erase this equilibrium word and I'll put it in the next line. So the equilibrium and sadly I can never remember if it's two L's in there, so I'm just going to go over that like I don't even care. Equilibrium condition or state. So when I say fully describe it, what I mean is it ice? Is the temperature 0 degrees Celsius? Is it ice and tea? Or is it just all ice? That sort of thing. So our solution, that's going to entail us using some very specific equations. Q equals MC delta T is one of them. Delta T equals T final minus T initial is another one. We can also say Q is equal to ML. That's another one. And we need our actual conditions and our initial state basically. So we know the mass is 1.00 kilograms. And then we know that the T initial, I should probably write it, T initial is equal to 20.0 degrees Celsius. And that's for, we're going to say it's iced tea, but in principle, if you start adding a bunch of sugar, things get kind of dicey. But if you're just adding, a tea bag or whatever, it doesn't appreciably change too much from water. So we can treat it just like water. So I'm just going to say the initial temperature of the tea, but realize it's actually the same. We're going to treat it like it's water, and I'm going to say the initial temperature of the ice is negative 15.0 degrees Celsius. Okay. And the mass M, the 1 kilogram, was a chunk of ice, so I'll put a ICE by it. And the mass of the T is 5 kilograms, so I'll say MT is equal to 5.00 kilograms. And I think that's just about it. Okay. Now, what we need to do is there is some possibility that we put so much ice in this tea that basically it freezes the whole thing. Okay. Or at least it brings the whole thing to 0 degrees Celsius. And then we have iced tea like we really want. So we really have to figure out exactly what's going to happen. Is all of the ice going to completely melt? Or is some fraction of the ice going to melt? And is very little of it going to melt, but bring it all to 0 degrees, all that kind of stuff. All of those are the different considerations we have to take into account. So the first thing we might want to do is figure out how much energy it's going to take to bring the water down to 0 degrees Celsius. In other words, bring the T down. So Q T to 0.0 degrees Celsius. That's going to be basically the specific heat of water, which is 1.00 calories per gram, or let's say kcal per kilogram Celsius degree. And then that's the actual C. Oops. I should probably write it in the way that I actually gave you the equation. So I should put the mass down first. So let's write the mass as 5.00 kilograms. That's the T. The specific heat should be 1.00 kilocalories per kilogram Celsius degree. And then the final temperature is going to be 0.0 degrees Celsius minus the initial temperature, which was 20.0 degrees Celsius. And when I do that, you're obviously going to get a negative number, but you can see it's 5 times 1, which is 5, times 20, which is 100. So this is going to be negative 100. That should allow me 3 sig figs. So I'll write this as 100.0 and I'll put a bar under that. And that should be kcals. So it's going to take about 100 kilocalories to take 4 kilograms. Yeah, that works. 4 kilograms down to 20 degrees Celsius, from 20 degrees Celsius down to 0. Now, in addition to that, I also want to find out how much energy is going to take to raise the ice from -15 to 0. So Q from -15 to 0.0. Okay, in this case, we're actually talking about ice. We know that the ice has a mass of 1.00 kilograms. We know its specific heat is 0.50. Now, again, I'm going to change it to kilocalories per kilogram Celsius degree. And we're going to bring that to 0.0 degrees Celsius from -15.0 degrees Celsius. Actually, yeah, yes, I was supposed to bring the ice from -15 all the way up to 0. So since I'm going from -15 to 0, this is actually going to be heat added, and I can see 1 times 0.5 is 0.5. Obviously, the 0 gives me nothing, but 0.5 times 15, a negative times a negative gives me positive. So this should be 0.5 times 15, which is 7.5. Now, technically, I only have 2 sig figs left, so I should leave it there, but I'm going to call it 7.50 positive K calories. Okay, so kilocalories, 7.50 to raise the water from to raise the ice from -15 to positive, or excuse me, to 0 degrees Celsius. Now, what's it going to take for me to actually melt all of that ice? Well, that's going to require Q equals ml. And for the ice, we could use, again, the latent heat of fusion, which was 79.7. So that'll work. So we can say, again, 1.00 kilograms times, in this case, it's going to be -79.7. Now, we are talking about, actually, we're actually talking about melting the ice, so I should make that as a positive. And you can see this is where the problem comes in. So, and since I'm actually talking about melting ice, I'm going to have to add heat to it, and that's kilocalories per kilogram. And obviously, this gives me 79.7 kilocalories. Now, I can also interpret these in terms of kilojoules by basically multiplying by 4.186. So 100 times 4.186 would be -418.6 kilojoules. And I only had 3 sig figs, so I'm going to underline that. 7.5 times 4.186, that gives me 31.39. Now that technically only had 2 sig figs, and it's actually 395, by the way, and that's going to be kilojoules. And then this one, 79.7 times 4.186, that again is 3 sig figs, and that gives me 333.62. Those are not sig figs, and that's kilojoules. Okay. Any questions on that so far?
What does the energy of the final one mean again?
Okay, that final one is basically the energy that you have to add to the actual ice. Once you've got it all the way up to 0 degrees Celsius, you have to add that additional amount of heat to make it turn from the solid state to the liquid state. Makes sense? All right, so notice the top number was negative and the bottom numbers are positive. In fact, in order for this to basically take place, what we want to find out is that top number, that 418.6 kilojoules, that's how much heat is going to have to be removed to bring the T down to 0 degrees Celsius. And I think you can see that if you add 333 and 31.39, you're not going to get anywhere near the full 418.6 kilojoules. So we're not going to bring the T down to 0 degrees Celsius. That's clearly not going to happen. Does that make sense? So what we are going to have is essentially, since we've got more than enough energy to melt the ice, we're going to have basically a mixture of tea and water that has a temperature somewhere between 0 and 20 degrees Celsius. And I would imagine it's a little bit closer to 0, obviously, than 20, then it's closer to 20. So that's what we're going to do, and we're going to work that out. Okay. So now that I've satisfied that, I'll say this tells us the T at 20.0 degrees Celsius has more than enough energy to completely melt the ice and bring it to 0.0 degrees Celsius or higher. Okay. So now I'm going to do the calorimetry part, and the calorimetry part is going to be handled by Q lost equals Q gain. So I take everything that's losing heat and I put those equations on the left, and everything that's gaining heat, I put those equations on the right, and I make sure all the terms are positive. So that's how I'm going to do that. So switching back to my red pen, what's losing heat is the T. So I'm going to have 5.00 kilograms of T times 1.00 kilocalories per kilogram Celsius degree. And that's going to have a final temperature that will be lower than 20 degrees Celsius. So since I need it to be positive, I'm going to say 20.0 degrees Celsius minus T final. Okay. Now the T is not actually going to change state or anything. So that's all the stuff that's happening on the left-hand side. In other words, the only thing losing heat is the T. Now, the only thing gaining heat is going to be the ice, and that is 1 kilogram. So I'm going to say 1.00 kilogram. Again, I'm not writing units anymore. I've got to bring that temperature up to at least 0 so we can get it to melt. So that's going to be, of course, the specific heat of water, or excuse me, of ice is 0.50. And again, that's kilocalories per kilogram. And then I'm going to bring it up to a final temperature of 0, which is greater than -15. So I will say 0.0 minus -15.0. And you can see now that that does, in fact, give me a positive answer, which is what I wanted. And now I'm going to have to basically melt that ice. So I'm going to, again, factor out the M since that's going to be common to all of them. And I'm going to say plus latent heat of fusion. In this case, I'm going to call it positive because all our terms have to be positive. That's 70.9.7 kilocalories. And now I have water. In other words, once I put in that 79.7, the ice has now been converted completely to water. And now I'm going to bring the water temperature up. So that's going to require another specific heat of 1.00 because it's now in the liquid state. And it's going to go from 0 to some new higher temperature. So I'm going to put T final minus 0.0 and then a square bracket after that. So I ran out of space again, but you can see that that was 0. Hopefully that's not that big of a deal. So on this left-hand side, I get 5 times 1 times 20. 5 times 20, of course, is 100. So this would be 100 kilocalories. And then 5 times 1 would be negative 5.00. And this time it's kcal per Celsius degree times T final. So that's the left-hand side. The right-hand side, I got 1.00 times. Now, when I multiply the 0.5 times 0, I get nothing. But when I multiply the 0.5 times positive 15, I get 7.5. So this is going to be 7.50. Now, you can see that that 0.5 was kilocalories per kilogram. And then I'm per Celsius degree. Then I multiplied it by Celsius degree. So this is basically kilocalories per Celsius degree, or excuse me, per kilogram, like that. That's what the one's going to come into play with. I have plus 79.7, and that is again kilocalories per kilogram. And then finally, 1 times TF is just going to give me plus TF, and then 1 times 0 is going to give me 0. So I'm essentially done there. Now I can say multiply through by the 1, and clearly, since it's 1, it's just going to become 7.50, 79.7, and TF. So I can now get all the TFs on one side. So what I'm going to do is add 5.00 TF to both sides. Okay. And I'm going to subtract 7.5 and 79.7 from both sides. And when I do that, I'm going to get 100 minus 7.5 minus 79.7. And that gives me 12.8. So now I have 12.8 kilocalories. Now remember, since I've already multiplied through by that 1, which was kilograms, that's why I just have kilocalories now instead of kilograms, but that's what's happened there. And now on the other side, I have 1 TF plus 5 TF, so that's equal to 6.00 TF, and that means our final temperature TF should in fact be, and remember the 6 in front of the TF is kilocalories per Celsius degree. So TF is going to be equal to 12.8 kcal divided by 6.00 kcal per Celsius degree. So I'm actually going to get degrees Celsius out of that. You see it goes into there by 2, and then you got 0.8 over 6, or 12.8 divided by 6 gives me 2.13. And in principle, the 2.8, all of those numbers, actually, no, this 12.8 is not a sig fig. So I should only call that 2.1 degrees Celsius. And that's the final temperature. Any questions on that? So that is actually pretty good tea. It's not quite to the level of 0 degrees, but it's pretty good. Of course, you've also diluted it because now you've got, 1/5 of the mass is pure water. So you obviously, if you were making such a thing of tea, you would want to make sure you had the tea a little bit stronger than you normally want it so that that watering process didn't make it too weak. Anybody have any questions on that? All right. So that's pretty much all the types of examples that you really need to worry about with regards to calorimetry type stuff. Your book then goes on to talk about evaporation. And of course, evaporation is relevant to, for instance, how your body works. So, for instance, evaporation is basically a process by which a liquid goes from a liquid state to a gaseous state. It's said to evaporate. In terms of our bodies, that is evolutionarily advantageous to us for us to actually sweat. So what happens is our body has excess water. That water and salt and various other things that are in it will bead out through your pores when you're hot. And that comes out at about 98.6 degrees Celsius, or excuse me, 98.6 degrees Fahrenheit. So it's essentially body temperature. But when it comes out, then the air and all the lower pressure and all that stuff is going to combine, and that's going to create a slightly different scenario for the water than the water had when it was inside of you. In fact, what's going to happen is the lower pressure and the lower temperature are going to combine so that the actual water molecules can change state from a liquid state to a solid, or excuse me, to a gaseous state. But in order to do so, they have to have some more heat added to it. So the water is going to come up on top of your skin. The air is going to cool it down lower and lower and lower because the sweat's going to come out pretty close to 98.6 Fahrenheit. But the breeze and all that stuff, especially if you're running, that's all going to make it cool down. And as that water cools down, the heat from your body can actually be stolen to cause that uh, water to break its bonds between the adjacent molecules, and they'll become the gaseous state and leave, having stolen some energy from you and therefore cooled you down. Okay, so that's kind of important. That's stuff to know. Evaporation cools is one of the physics principles it gives you. It says physics applies, evaporation cools, and it gives you a number up here. For instance, it says the latent heat to change a liquid to a gas is needed not only at the boiling point. Water can change from liquid to a gas phase even at room temperature. This process is called evaporation. So notice the difference is it's not happening at the boiling point, it's happening at whatever temperature. The process is called evaporation, see section 18.4. The value of the heat of vaporization of water increases slightly with a decrease in temperature. At 20 degrees Celsius, for example, it is 2,450 kilograms per kilojoule, or per kilojoule per kilogram, or 585 kilocalories per kilogram, compared to 2260 kilojoules per kilogram, or 539 kilograms per kilocalories per kilogram. So in other words, it went from 539, which was the heat of vaporization at the normal boiling point. But when you do it at 20 degrees Celsius, it's actually not 539, it's more like 585, which is actually better for us because as we are trying to sweat, the more energy it takes away from us to evaporate that sweat, the more energy that's taken away from us so that we can cool. Okay. Any questions on that? So that is the evaporation process. So you're mostly getting that area for concepts, but you can see, for instance, they could give you a problem and say how much energy is going to be required to evaporate a certain amount of sweat on your body. If your body's at 20 degrees Celsius, you could refer back to the book and see that it's 585 kilocalories per kilogram instead of the 539, and you could use that. Then it goes on in the section 19.5.2, which is the kinetic theory of latent heat. It says we can make use of kinetic theory to see why energy is needed to melt or vaporize a substance. The vaporization process is a more energetic reorganization of the molecules than is melting. The average distance between the molecules is greatly increased, and hence the heat of vaporization is generally much greater than the heat of fusion for a given substance. So that's some of the conclusions they were able to make from thinking about that kinetic theory, which remember we used at the beginning of chapter, I think it was the beginning of chapter 19, but no, it's the beginning of chapter 18, when we use the kinetic theory to find out that 3 halves kT is the average translational kinetic energy of molecules. So, any questions on that? All right, so we're now going to go into the first law of thermodynamics. So this is the point where I'm going to say, okay, it's 6:22. Let's take a break till 6:30, and I'll stay right here in case anybody has any questions. But we'll finish the chapter when you come back. So come back by 6:30, and feel free to ask me questions if you wait here while I'm here. I just want to make sure I give you guys a break because I always forget to. Got about 2 more minutes. All right, got about 1 minute, everybody. Okay, it's time to get back started. So this is the last example we just worked. That was example 2. I want to offer again, does anyone have any questions about that before we move on to the next topic, which is the first law of thermodynamics? I do have the chat window opened as well. I do not see anybody writing in there, but I just want to let you know in case anybody wants to try to address it that way as opposed to speaking out. Uh, I just realized that my I and my N are so close together, they look like a W down here. So that looks like Galwed. Don't like that. Good enough. All right, so let us start with talking about the first law of thermodynamics. So the first law of thermodynamics is really a statement of conservation of energy. So you can imagine that you can take a system and you can either add heat to it, or you can take heat away, or you can do work on it, or you can make it do work on its environment. That's pretty much the types of systems we deal, or the types of actions we deal with in thermodynamics. Now, later we'll actually link this to mechanical energy, so you can have a connection between conservation of energy that we learned about in, let's say, chapter 7 and 8, as well as this conservation of energy that we're learning here in the second law of, or excuse me, in the first law of thermodynamics. But what you want to think about here, and this is different from what you're learning, what you learned in chemistry. So if you had chemistry already, even at the high school level, you probably learned a first law of thermodynamics, and you learned it a little differently. What we're doing when we talk about the first law of thermodynamics in physics, we generally say change in internal energy, delta E internal. So E internal is the center, is the symbol we use for internal energy. And what we're going to say is if you actually add heat to the system, then that will increase the internal energy. That's not the only option. For instance, if you figured out a way to take an ideal gas and add heat to it without it changing its temperature, then that work or that heat must go somewhere else, because it obviously, the internal energy for an ideal gas only depends on the temperature. So if you actually added heat to it, and the internal energy did not go up, because the temperature didn't go up, then where did it go? Well, what we do is we say it could also go into doing work. And what we normally talk about, instead of the work done on the system, which Q here is the heat added to the system, we say the heat done by the system or excuse me, on the system is Q, and the work done by the system is W. So we actually have to do minus W. So it's important that you understand in this terminology, Q greater than 0 implies heat added to the system. And W is work done by the system. So if W is greater than 0, that means work, or that means system has done work. And if W is less than 0, the system had work done on it. Okay, so that's the key difference. So when you study this, and for instance, in chemistry, more than likely you had Q plus W, and that's the difference. Okay, we often sometimes will say dE internal is equal to d bar Q minus d bar W, and that's acceptable as well. What I want to point out to you is that we're using D for the E internal because that's an actual differential. Okay, whereas the d bar Q and the d bar W are infinitesimal changes in or infinitesimal amounts of heat added, or infinitesimal amounts of work being done by the system. The difference being that a real differential you can integrate and get back E internal, whereas a D bar you can't integrate. Okay, there's no Q function that you can integrate D bar Q to get, and there's no W function that you can integrate D bar W to get. So that's the big difference there. And this has to do a little bit with, for instance, last semester when I told you about conservative forces and how, if one thing was true, then you get all these other things that are going to come true. Well, we'll investigate that again when we get to the electricity and magnetism part. So if you had the 241 course under someone else, you might not have had that explained to you, but we're going to do it again later on, so it's okay. All right. So that's really what the first law of thermodynamics says. And as I said, you can actually talk about mechanical energy as well. And if you want to take that into account, you can generalize it and then say another form is delta K, which remember that's kinetic energy, plus delta U, which remember that's potential energy, plus delta E internal is equal to Q minus W. And then that's the equivalent of conservation of energy. Okay. So just to get a really easy problem out of the way, I've written example 3 here. It says, it has been found that when you add 3,000 joules of heat to a system, the atmosphere does 2,000 joules of work on the system. What is the change in internal energy for the system? So this is really a point where you can actually see exactly what we mean by W being work done by the system and Q being heat added to the system, assuming they're both positive. We are using delta E internal is equal to Q minus W. We're actually saying that Q is equal to when you add 3,000 joules of heat. So Q is equal to positive 3,000.0. And notice I put the decimal there specifically so there would be no ambiguity as to the number of sig figs. That's particularly problematic because now I have a 5 sig fig number. Now, in addition to that, we found that when you added that much heat to a system, the atmosphere did 2,000 joules of work on the system. So in that case, the W is negative, and we get W is equal to negative 2,000.0 joules. Again, another 5 sig fig number. So delta E internal in this particular case is equal to 3,000.0 joules minus negative 2,000.0 joules, and minus a negative is the same thing as plus a positive, which we often write by doing that. And in this case, we get that the answer is 5,000.0 joules. So basically, that should make some sense to you. Remember, the internal energy is the total energy of all the atoms / molecules in the object. So the object being what we're calling system here. Now, if I add 3,000 joules of heat to it, that energy in general is going to distribute itself among those atoms or molecules over some period of time until it reaches equilibrium. And that generally results in the average kinetic energy of all the different types of kinetic energy increasing. So not just the translational left, right, in, out, up, down, which corresponds to temperature, but the additional ones, which could be molecules vibrating this way, rotating that way, all that good stuff. All of that goes into increasing that. So we would expect that 3,000 joules to actually increase the internal energy. Now, additionally, it said 2,000 joules of work was done by the atmosphere. So you can imagine, for instance, the system might be a little bit of gas in a cylinder. And then on top of the cylinder is a piston. And the atmosphere, once we added that heat, somehow the atmosphere pressed down on that piston and did work on it. That work would be PDV, is what we're ultimately going to learn. We haven't learned it yet, but we will learn it. That work actually went into the system. So it actually was work done on the actual gas inside the cylinder, if we're using that as our system. And you'd expect that too to actually increase the energy of the atoms / molecules in the system. So both of those should have made the net internal energy higher. And that's exactly what we got. We got that the net internal energy went up by 5,000. Does that make sense? Now, if you were, and in fact, your book does a very similar example called Exercise E. If I make it similar to my own problem, then I'd say, what would be the internal energy change in this example if the 3,000, or excuse me, if the 2,000 joules of, it was heat added was 3,000 joules. If the 3,000 joules of heat is added to the system and the 2,000 joules of work was done by the system. Anybody want to tell me what that answer would be? So what would be the internal energy change if the 3,000 joules of heat was still added to the system, but the 2,000 joules of work was done by the system instead of on the system? Exactly, Ethan. You would actually have to do, in that case, the work would be positive. So you'd have 3,000 minus positive 2,000, which gives you 1,000. So that's exactly right. Any questions on that one? All right, so that should be like the most rudimentary first law of thermodynamics problem you could possibly do. You could actually convert kinetic energy into thermal energy. So, for instance, if a let's do this one. I'm going to do example 4. So this is example 4. A 5.00 gram bullet is shot into a tree with a speed of 450.0 meters per second and exits the other side at 200.0 meters per second. Oops. Where did the lost kinetic energy go? Okay. So in this case, we're using the more generalized version of the first law of thermodynamics. Kinetic energy is equal to 1/2 mv squared. That's going to come in handy. We also know that delta K plus delta U plus delta E internal is equal to Q minus W. And we know that V initial is equal to 450.0 meters per second. We know that V final is equal to 200.0 meters per second. We know that the mass is 5.00 grams, which equals 0.00500 kilograms. Okay. So we can write it out as follows. We're going to say 1/2 m. Now I'm going to put parentheses around here and say this is V final squared minus V initial squared plus 0, because I said that a bullet was shot into a tree. I didn't necessarily say I was shooting it down or up. And if I did shoot it in a downward direction or upward direction, that would cause a change in potential energy. And I'd need to give you that information, not only that I did that, but also how far down and how far up I shot it. So that means we have to go on the assumption that potential energy change was 0, which is why I wrote delta U is equal to 0. And then I'll say plus delta E internal is equal to Q minus W. Okay. So when I go to do that, I'm going to say 1/2 of 0.00500 kilograms times 450.0 squared minus 200.0 squared is plus delta E internal is equal to Q minus W. So when I do this, 450 squared minus 200 squared, that gives me essentially 162,500, which should have 4 sig figs. So that's, let me go ahead and multiply that by, yeah. So that gives me to the nearest hundreds place. Now I'm going to multiply that by 0.005 times 0.5. And that gives me 406.25 joules. And that's one extra sig fig there. Okay. Plus delta E internal equals Q minus W. Okay. So that's the actual loss in kinetic energy. And in this case, there's really no work done on the system. If you take the tree and the bullet as our system, then basically what happens is No potential energy is involved. No work is done on or by the system by outside forces. That's why I had to specify that the tree and the bullet were the system. Okay. Since the tree and the bullet were the system, you don't count the work done on the bullet by the tree as work. So that's just left out. So no work is done on or by the system by outside forces, nor is any heat added because of energy, because no energy was transferred to or from the system due to a temperature difference outside of the system. Thus, the kinetic energy gets transferred into internal energy of the bullet tree system. So, in other words, what we're saying here is this quantity is zero, this quantity is zero, therefore, delta E internal is equal to negative 406.25 joules. And that's what happened. So the total internal energy of the system, in some sense, went down by negative 406.25 joules. And that's basically because, yeah, what you do notice is if you actually stuck your finger in the hole that was left by the bullet, you'd probably find the trees a little hotter. And you, of course, would find the hole through the tree. That's another thing, but you can't really account for those. So, what we know is obviously because it lost that much kinetic energy, that much kinetic energy must have went into a decrease in internal energy. Any questions on that? Ooh, I did the backwards forward. Oh, no wonder the negative. The negative was bothering me. Notice I actually did it in the reverse order. So let me fix that real quick. I can't believe I did that. I apologize, everybody. I was just sitting here thinking that negative is wrong. And the reason why is because the final velocity was 200. So I'm going to write this in here. And the initial velocity was 450. So I'm going to erase that. Notice I put it in a different color so you'll know exactly where my screw up was. Okay, so this ends up becoming over here a negative 406.25. And then this over here becomes a positive 406.25. That makes more sense. Okay, as I was telling you, the tree would actually heat up, and that's actually where you'd say that went because the tree heated up. The bullet heated up as well. The bullet got mangled a bit, that sort of thing. So all that goes to increasing the internal energy of the system. Sorry about that. I just was like not paying attention and didn't even think about the negative. But anyways, anybody have any questions on that? Thank you, by the way, Ava. I see you would have saved me embarrassment by telling me the right answer with that. So I appreciate it. I wish I would have read it quicker, but yeah, I do appreciate you doing that. That's awesome. Anybody have any questions? Well, that was a boneheaded thing I did. Oh well, let's move on. So the next process are things that we need to talk about are processes specifically from thermodynamics. So what I will tell you is I'll remind you again that thermodynamics is really a science that's about a lot about derivatives, but it's also a lot about terms and definitions. So one of the first things you do when you take a thermodynamic class, whether it be engineering thermo or physics thermo or steam table thermo or any of those kind of things, is you got to learn a ton of definitions. Like a system is the thing that you're interested in. An isolated system, in general, is a system that's completely away from everything. A closed system is a system that doesn't allow objects in or objects out, so you can't, for instance, increase mass or decrease mass, that sort of thing. Adiabatic system is a system where heat is neither transferred into the system or outside of the system. Bunch of little rules like that. So I would highly recommend, for instance, we have a test on chapters 17 and 18 coming up Thursday night for you guys. So in chapter 17 and 18, I'd make sure I'd basically write down a good definition for every boldface term you see. And of course, now that we're covering 19, that won't be on the test, but you should do that for chapter 19 as well. So just go through there and pick out those definitions. And I'll tell you that a lot of the definitions come down to processes. So, for instance, when you let a system absorb heat, then that is a process. That happens to be a non adiabatic process because the system is taking in heat from somewhere else. You can represent those processes as a series of equilibrium states. And if you can do that, if you can actually represent the changing of a system as a series of equilibrium states, then you can take time to actually graph, say, pressure versus volume, or pressure versus temperature, or volume, excuse me, or volume versus temperature. All those are able to be done. Another process, as I said, was adiabatic, was when Q is equal to 0. So in the first law of thermodynamics, it says delta E internal equals Q minus W, and Q is heat added to the system. So an adiabatic system means Q equals 0. If it's an isothermal process, that means delta T is equal to 0. Huh, sorry. That means delta T is equal to 0. So some way the system has been held at a constant temperature. Uh, there are processes called quasi-static, which means almost static. And static means basically it's moving really, 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 really slowly. And another thing of looking at it is it's a series of equilibrium states that are only differentially different from one another and going from one to the next. A heat reservoir is basically what we call a heat sink, like the Earth is a heat reservoir for our geothermal heating and air conditioning systems, because us humans are such a small, insignificant part of the surface of the Earth, which is part of the reason I initially did not believe global warming, for instance. And then I studied it a lot and figured out, oh, okay, maybe it is real, or definitely it is. But anyways, so the Earth is, for instance, a heat reservoir for us, and what that means is we can add heat to the Earth, heat to the Earth, heat to the Earth, keep adding heat, and adding heat, and the Earth's temperature will not change internally. Okay, so if I make a bunch of geothermal systems and I distribute them around a neighborhood of 10,000 houses, you'd probably find in that neighborhood, maybe right, if all of them went to essentially the same depth, you might find that the temperature at that depth might have actually increased a little bit, at least in that small area. But it's likely that it wouldn't have increased at all. And if you go further down into the reservoir, or below the reservoirs, what you'd find is down there the temperature hasn't changed at all. And that's really the more important thing, is the layers that it has access to are not going to appreciably change temperature, no matter how much heat you put into it or how much heat you take out of it. That's called a heat reservoir. Everybody get that? Does that make sense? Okay. Uh, if you do, for instance, a system, if you take a system that's maybe a gas confined to a cylinder with a piston on it, and you hold it at constant volume, then it turns out the work we do is the integral of PdV. And since the V can't change, in that case, a constant volume process would mean work would be 0. So those are some of the ramifications we'd run into. Another ramification, for instance, for an isothermal process is if you're dealing with an ideal gas, then the internal energy is not going to change. So delta E internal equals 0 because T doesn't change. And obviously, if you've been reading your book, you should already know by now that for an ideal gas, the internal energy only depends on the temperature. So if the temperature doesn't change, the internal energy of an ideal gas can't change. So your book talks about a lot of that all through section 19.7. Isothermal processes, which means delta T equals 0, quasi-static, it talks about heat reservoirs. It talks about PV diagrams and stuff of that sort. And it even gives you a figure of a P versus V diagram where you see the curve for the series of equilibrium states goes along the P axis and then starts to go out along the T axis. And if you do a higher temperature one, that's actually going to have a higher pressure for a given temperature. So it's the same line, but a little bit higher. That's what a graph would look like for P versus V. And then it goes into the next section, which is adiabatic processes, and it tells you Q equals 0. And they give you a plot of P versus V. And in that case, for isothermal, you get one graph, and for adiabatic, you get another. So let me show you what I mean by that, because I'm thinking you guys are probably not looking at the book right now. So for instance, if I say this is my P axis and this is my V axis, then you could say an isothermal process is a, well, let's write it right here. Now, if you look at a PV diagram, what you'll find is it looks something like this. Okay. And then you could find another one. This is at temperature T1. And then you could find another one that looks like this. And this is at temperature T2, which is greater than T1. Okay. Now, this corresponds, for instance, to PA, and this might correspond, for instance, to VB. Then this would correspond to PB, and this would correspond to VA. Similarly, you could say this corresponds to P1, V1, and this corresponds to V2, P2. So those are various things. And you can see that this graph with the T1, T2 being higher than T1, that's completely consistent with PV equals nRT, because pressure is equal to nRT over V. So you can see for a higher temperature, T, the P should be larger, which is exactly what T2 greater than T1 means. Similarly, we can draw another graph, and this will be P versus V again. And we could have a state A that two different graphs lead from. And in fact, this one could be an isothermal process, which, remember, means delta T equals 0. And this is from A to B. So I'd call this position B there and that one A, and I put a purple dot there. But you could also have an adiabatic process, and that's what that would look like. And that is Q equals 0. And you should be able to convince yourself, for instance, that, hold on a second, from A to C, you should be able to convince yourself that when the process is adiabatic, the graph of P versus V would actually be lower than the graph of P versus V for a isothermal process. Okay, because when you can actually not add any heat, like you could with the isothermal process, if you do add heat in the isothermal process, and you look at P versus V for that isothermal process, the temperature is locked down, so you can sort of think of that as E internal, delta E internal is equal to 0. That means any heat added will go completely to work done. And in order for all that to go to work done, you need a larger area under the curve, specifically because work equals the integral of F dot dl, which we can write as the integral of pressure is equal to force divided by area. So force is equal to pressure times area times dl. But that right there, A times dl is dV. So you get the integral of P dV. So you see the area under the curve is the actual work done. Since it's isothermal, every bit of heat added has to go into, based on the first law of thermodynamics, delta E internal equals Q minus W. Isothermal for an ideal gas and most gases. The isothermal process has delta E equals 0. So this implies Q equals W. So every bit of heat added has to go to work, and that would be written as area under the curve for a P versus V diagram. If, on the other hand, it's adiabatic, then you have delta E internal is equal to Q minus W, only Q is 0. So every bit of the change in internal energy would go into work being done, or work being done would go into internal energy, and you'd expect that to be a little less because you're not getting any internal energy from any energy inserted inside of the system by yourself. Okay, so hopefully that convinces you that the curve would be a little lower. That's certainly something to work on. Then they go on to talk about an isobaric. So there's an isobaric process. And isobaric, think bars as units of temperature. That means delta P is equal to 0. And then there's isovolumetric, also called isochoric. This one implies delta V is equal to 0. So that's another process. And in fact, you can represent it on a P versus V diagram very easily. There's V, there's P. That's isobaric. And then I can do a P versus V diagram for isovolumetric, and you'd see there's A and there's B, and that's a vertical line. Makes sense, right? Once you have all those definitions worked out, and you have this idea of work is equal to the, what are you doing in here, buddy? You're not supposed to be in here. Once you have this equation right here and these ideas, then you can start making sense of the processes. And that's what we're going to do now. Okay. So if you, for instance, have work for an isothermal process, I'm going to show you an example. Let's say, what is the work done on an ideal gas when it is, actually it's work done by the ideal gas. That's what I want to do. Yeah. So I'm going to say work done by instead of on. So let me change that real quick. An ideal gas when it is expanding from PA VA to PB VB, where VB is greater than VA and PB is less than PA. Okay. So I'm just going to draw this out with a graph real quick. So Let's draw my line for this axis and then my line for this axis. And then this axis is going to be the v-axis and this axis is going to be the p-axis. And I will draw the actual graph of the gas. And what I'm going to say is this quantity right here corresponds to PA, and this corresponds to VA. And then let's say this one right here corresponds to PB, and this corresponds to VB. Then work is equal to the integral of P dV. And from the ideal gas law, we know PV equals nRT. And this is supposed to be an isothermal process. When it is, okay, yeah, I have to write that here. Isothermal, expanding isothermally from that to that. So with that in mind, we can see that P is supposed to equal nRT over V. So I can say now N times R times T over V times dV. But since it's isothermal, the N, the R, and the T, and we're also assuming it's a closed container, I can write the N, the R, and the T outside, and then I get the integral of dV over V, which equals the N, which equals nRT, actually times the natural log of V, and that's going to go from VA to VB. So I get N times R times T times the natural log of VB over VA. And that's the actual formula for the work done. Any questions on that? And what it represents, by the way, is the area under this curve. Okay. Now, what about the work done? Oh, yeah, let's do something like this. So your book does a nice little example, and it's sort of building on the one we just did. So this is going to be V, this is going to be P, this is going to be A. Ooh, I should probably put that a little further over. So I'm going to put this right here and then put this other one right here. And I'm going to say the isothermal curve goes right through there. So this curve is called an isotherm. And we're going to call this point A, and we're going to call this point B. And we're going to go on the assumption that we're traversing it that way. So basically, something is causing the gas to expand from volume A to volume B. And then after that, the the system contracts. And this time, what kind of process is that horizontal line? Can anybody guess what that is? Notice it has it's horizontal, so whatever the vertical axis is going to be a constant, and that should mean, of course, that it's isobaric. And now it's going to go straight up, in other words, vertically, back to there. What kind of process would that be called? Anybody want to take a guess on that one? So that one is vertical. So that means the horizontal axis variable is a constant, and that means it's isovolumetric. Okay. So if we wish to actually calculate, for instance, the entire work done and going around that loop, then that area would be the work done. And in this case, it's just the area inside of here. Okay. So the total work in this case, W from A to B to C to A again, would be equal to the integral of P dV isotherm plus the integral of P dV isobar plus the integral of P dV isochore, because that's a smaller word, I chose to write that. So we already know what happens with the isothermal one. We get N times R times T times the natural log of VB over VA for that first term. And then for the second term, notice the P is a constant, so that becomes plus P times, now it's going to be VB. And notice VC and VA are the same thing. So I'm going to say VB minus VA. And of course, the pressure here is the pressure at B because it's isobaric. So that's that part. And then the isovolumetric part would be plus 0 because the dV is 0. And that's because it's isochoric. So that would be the whole answer here. You'd be P times delta V for the isobaric part. It'd be P nRT times ln B over, oops, by the way, I wrote A there, but I didn't write the I wrote the subscript, but without the actual volume. So it should be VA down there. So that should be the area inside the curve. I'll just call it area inside. Any questions on that? Okay, I'm looking for something else here. Let's do this example. So this example, we're going to say, what example am I on? I didn't actually number that last example. So we had example 4 and we're now up to example 5. Let's say example 5. An ideal gas, I don't know why I capitalized it. An ideal gas is slowly compressed at a constant pressure of 3.0 atmospheres from 10.0 liters to, let's say, 1.50 liters. This process is represented by basically the graph we just did. Oh, hold on. No, it's not that one. I'm looking for the figure. Okay. Yeah, that's it. Okay. Is represented by the last graph. As the path from B to C. Okay. In the process, some heat flows out of the gas. Some of the some of the heat flows out of the gas. Ah, man. And then heat is added to the gas, holding the volume constant. And the pressure and temperature are allowed to rise. Now this part goes from, if we look at that, that goes from C to A. Until the temperature is at the original temp. Okay. We want A, calculate the total work. And B to C to A. And then part B, calculate the total heat flow into, darn it, the gas. Okay, so that's a pretty big problem, but basically we're attacking what we just did, so it shouldn't be too terribly hard. What we're first going to do is start off in the constant pressure phase. And of course, with the constant pressure phase, we had that was from B to C. Work is equal to the integral P dV, but P is a constant. So we get, in fact, that the pressure is going to be 3.0 atmospheres. And the change in volume is going to be from 10 liters to 1.5 liters. So what we're going to do is we're going to say this is equal to P delta V, and that's 3.0 ATM times 1.01 times 10 to the fifth Pascal is equal to 1 atmosphere. And then delta V is 10 minus, actually, we're going from 10 liters to 1.5 liters. So it's actually going to be a negative, and it should be a negative, what, 8.5? Now, I can't really use liters to do that because a liter uh, is, in terms of cubic meter, uh, is what I need, because when I multiply joules, or excuse me, pascals times cubic meters, that actually gives me a unit of work in joules. So I've got to change that one as well. So I'm going to say the work is actually equal to 3.03 times 10 to the fifth pascals times negative 8.5 liters, and 1 liter basically is equal to 10 to the third, or 10 to the negative third cubic meters. In other words, 1,000 liters is a cubic meter. So that should give me an actual negative amount of work done. So 3.03 e to the fifth times 8.5 e to the negative 3. And that gives me negative 2.575 times 10 to the 3. That should be 576 technically. Times 10 to the 3 joules. And that's one extra, actually, that's 2 extra sig figs. And that looks horrible, so I'm going to make that better. Or, okay, so that's the work done in that first part. Now we got to do the work done in the other part, but the work done in the other part has no change in volume. So we can say work done from C to A is actually equal to 0. Okay. And then, of course, the total work done, let's see, during the compression, B to D. Yeah, that works. Negative 2.576 times 10 to the third joules. Work from C to A is that. And what we were asked to calculate is the total work in going from B to C to A. Let me double check that. Yeah, B to D to A. Okay. So now I can go ahead and calculate what work is done from A to B. So if we look back here, what we've done is, there's supposed to be a way I can do this. Let me see if I remember how. Nope, that's not it. Oh well. That isobaric part was what we just did, and then the isovolumetric part we also did. Now we're supposed to do the part from A to B, and that was the isothermal part, which we already got the answer for. So I can say work. Darn it. I can say work from A to B is equal to nRT natural log VB over VA. Now, what we saw is that was the actual compression, or excuse me, expansion, where we went from the volume at A, which was the 1.5 liters, to the volume of 10. So we went from 1.5 to 10. So in this case, it's going to be an ideal guess. Did I tell you how many moles? I don't think I did. I did not give us the number of moles. An ideal gas is slowly compressed at constant temperature. Trouble through that. That did that. That did that. Okay. So what we'll say is this is going to be N times R times whatever the T was, that's T, times the natural log of VB, which of course is the larger volume, which is the 10.0 liters over 1.50 liters. So that's actually the work done in that part, but we can't necessarily figure that out because we don't have N or R or T. But we do know it's a system, and we do know that the total internal energy, since we went in a complete loop, the total internal energy has to be equal to the change in internal energy has to be equal to 0. So we can use that to actually work out what our looking at the wrong thing now. Actually work out how much heat was added. And of course, since the total internal energy is 0, that means Q is equal to 0. So cyclic process, let me write this in a different color. Cyclic process implies I went from B to C to A to B again, implies delta E internal equals 0. And that's true, period, not for just an ideal gas. That's just true, period. And the first law of thermodynamics says that delta E internal is equal to Q minus W. So delta E internal equals 0 implies Q is equal to W. So we should be able to figure out from that exactly how much heat is added. So if I want to calculate the actual heat, then I have to actually calculate the work done. The total work done, of course, at least in that isobaric process, is 1600, or excuse me, is the number I just got, which is negative 2.5 or negative 2.6 times 10 to the third joules. So ultimately, we can say, I want to make sure I read this right. So, I was writing it down, but I want to make sure I wrote everything right. It says an ideal gas is slowly compressed at a constant pressure of 3 atmospheres from 10 liters to 1.5 liters. This process is represented by the last graph as the path from B to C. In the process, some heat flows out of the gas, and then heat is added, holding the volume constant. And the pressure and temperature are allowed to rise until the temperature is at the original temperature T. Calculate the total work T. Oh, okay. Well, wait a second. Since the temperature is the same at A and B. Now, remember our graph looked like this. I'm just going to quickly do a graph. We did like this, and then this, and then this. So TB and TA are equal to each other because that's an isotherm. In other words, that little graph's an isotherm. So TA is equal to TB. So I don't even have to go all the way around to say delta E internal equals 0. Going from, since I treat it as an ideal gas, going from B to C to A, that implies delta E internal is also equal to 0. And that means Q is equal to W. And I've already calculated that W is 0 here. So let me, W equals 0. And here W is equal to negative 2.576 times 10 to the third joules right there. Okay. So now I can say Q is equal to negative 2.576 times 10 to the third joules. So that's the answer for that part. And this part, this part is actually equal to the work done. And I can circle that off like this. Okay. So now we're done. That's basically it. Anybody have any questions about that one? That was a little harder. Sorry, I got kind of confused in the middle because I was looking at two different problems when I was trying to make that up, and stuff got a little nasty. But hopefully that settled it for you. So this is the kind of stuff you need to be able to do with all these different processes. Not only that, you'll see that there's several examples that can be solved. They then go into a free expansion. Now, with a free expansion, in general, that's supposed to be a expansion of a gas into a bigger volume, but that bigger volume should have zero pressure in it, so it doesn't take any work to actually go in there. And that should be something that requires a zero change in internal energy. So in a real gas, there is actually a slight change, but in an ideal gas, the change is zero. And from that, you can then use it to help you figure out things like the temperature won't change and the work is equal to the heat added, so on and so forth. But anyways, your book does talk about that. And then it starts to talk about molar specific heat. So I think I'm definitely going to cover this yet a third day instead of just 2 days, and we'll call it after that. So I'm going to do another day of discussing this. We're a little bit early. We still have 15 minutes left. So I'm going to go ahead and start talking about the next topic, which is specific heat of gases. If you actually look at the specific heat of gases in terms of calories per kilogram or gram Celsius degree or something like that, you'll find that they're quite erratic. But if you look at the molar specific heats for gases, they're actually quite fixed. So I'll say it this way. The specific heat are specific heats of various gases measured in calories per gram Celsius degree or joules per kilogram Celsius degree are, or I should say, vary greatly. However, if we look at the molar specific heats, which is measured in calories per mole Kelvin, we find nice patterns. So for instance, if we look at helium gas, this is monatomic. If we look at helium gas, we see that, for instance, lowercase cv and lowercase cp measured in the appropriate values is actually 0.75 and 1.15, and both of those are measured in kcal per kilogram Celsius degree. Hey, Allie, you okay, baby? But if we look at the molar specific heats, which are listed as capital CV and capital CP, Then we get 2.98 and 4.97, and those are measured in calories per mole Celsius degree. Now that doesn't look like much because we only have one value. But now if I look at a second one, which is also monatomic, in this case I get 0.148. Ooh, could have done that a little worse. 0.148. And then for the other one, I get 0.246. And of course, that has the same units. But when I go over here, I get 2.98 and 4.97. Okay. Now, if I go to diatomic, we could look at, for instance, N2 and O2. And in this case, I get 0.177 and 0.248, again with the same units. And for O2, I get 0.155 and 0.218, again with the same units. But if I move over to the molar one, I get 4.96 and 6.95. And here I get 5.03 and 7.03. So you can see the two values N2 and O2 for CV have very consistent values. 4.96 is really close to 5.03, and 6.95 is really close to 7.03. So that's an advantage. If I look at triatomic, and of course that would be something like CO2 or water. Okay. In that case, I get 0.153 for CO2, 0.199 also for CO2, but for water, I get 0.350. Notice that's significantly different. 0.489. Notice that's significantly different as well. When I go over to the molar ones, though, I get 6.80 and 8.83. And when I go for the same one for water, I get 6.20 and I get 8.20. So you can see they're very close to each other again. And polyatomic follows the same suit. So it turns out it's just much better for us to use molar specific heats when we're dealing with ideal gases as opposed to liquids or whatever. So in doing so, we can actually come up with some really neat results. What I will tell you is what we're now going to use is we're going to say Q is also equal to the number of moles times capital CV delta T. And of course, that means volume constant. I think I mentioned that last time. If I didn't, that's why I'm subscripting them with V's and P's. So the specific heat at constant volume means that the specific heat has been measured in such a way that the volume was held constant, whereas the CP, the pressure was held constant. So if you can imagine, if you put heat into a gas, that heat can go, according to the first law of thermodynamics, that can go into the internal energy by increasing the temperature, but it can also go into doing work. So if you actually do add heat at constant volume, no work can be done. So all the heat's going into changing the temperature and internal energy total. And of course, the C is supposed to be a measure of how much it takes to change the temperature. So the CV should actually be a smaller quantity because none of the energy goes into work. It all goes into changing the temperature just about. Whereas CP would be, of course, bigger because some of that energy would go into doing work. So that's what we're doing here. And we also have Q is equal to N Cp delta T, and that's pressure constant. So here's two new equations that we want to make sure we use. And when we go to use that, that's nice. We can actually see that, for instance, CV, the constant pressure, is actually just the molecular weight of the substance times lowercase cv, and CP is actually the molecular weight times lowercase cp. So if you want to figure out how to get the molar one, you just have to multiply it by the molecular weight, which you get from the periodic table. So that gets that. Now, if you actually have a constant volume, when you're doing that, then the first law of thermodynamics changes a little bit. Constant volume means delta V equals 0, which means W equals 0, which means delta E internal is equal to Q minus W, but W is 0. So what that means is Q at constant volume is just equal to delta E internal. But we also know that if you did it for constant pressure, you could say when you do that, then what you have is delta E internal is equal to QP minus W, which equals QP minus P delta V. Therefore, you get QP minus QV is equal to P delta V. In other words, I use the fact that the change in internal energy is just QV, and now I've got this neat new expression that can help me. QP minus QV is equal to P delta V. If I use the ideal gas law, PV equals nRT, then I can change basically the in this case, I can actually change. Oh no, if I do that, then I can say QP, which is N CP delta T minus N CV delta T is equal to P. Now, and the delta V is going to be N times R times delta T over P. So I end up getting basically that. Whoa. Notice I have a constant P, for instance, on the right that cancels out with a P, and I've got a N and an N and an N in all three terms, and a delta T, and a delta T in all three terms. So I end up getting this nice little result that CP, darn it, almost done here. Hold on. That CP minus CV is just equal to R. And that is what I was shooting for. Next, I'll actually figure out what CP and CV are independently, but that's it. Time's up. If you have any questions, just stick around. I will not leave until the last person leaves. So by all means, ask me questions. But have a good evening. Start taking your practice test over and over. Remember, you have an online face-to-face, or excuse me, an online test that's due Thursday by 2:15 p.m. And then you have a face-to-face test that happens at 2:15 p.m. Ideally, you wouldn't necessarily want to do that test just before the face-to-face test, but that's how long you have. And remember, I only take your highest score. So once you get 100, you can still keep doing it to practice. and it's still going to stay 100. So have a good one. Don't forget to install your lockdown browser. If you're planning on using your computer at least at the face-to-face test, you want to download the lockdown browser. If you've already had it download, click on the lockdown browser anyways, because you probably need to update it, and that's an important thing to do, or otherwise you'll have to waste a lot of time doing it when you get to your face-to-face test. But thank you, everybody. Have a good one.
Uh, I had a question about, I guess, my test for tomorrow.
Uh-huh.
I'm in your in-person class, and you said, and I know I enrolled in this class late. I remember you telling me like the first day I spoke to you that I could take it a little later.
Yeah, you can, definitely. That's not
Yeah. Is there like a specific day that you have in mind?
since you were a week late, I can give you up until Thursday of next week to do it.
Okay, Thursday. That's cool. That's cool. And where would I take it? Because I know the test is tomorrow during lab time.
Right. So you don't have to show up to lab at all tomorrow for that. And you shouldn't talk to other students about the test because I will try to make it as comparable to theirs as it can be. So that means some of the questions might be somewhat similar. So you don't want to talk to them and they don't want to talk to you. But you can take it at a testing center at whichever campus is nearest to you.
Okay. Wait, so is it online, so like lockdown browser?
You do a lockdown browser just because they're monitoring you. If you do it at the testing center, they're automatically monitoring you, so you can't check it, but you can use the lockdown browser there as well.
Okay.
They
Okay, yeah,
watch
that
it on
was
your screen when you're at a testing center. So
oh, because they're watching the computer.
yeah,
Okay, yeah. Is it the testing center in the
it's in the
uh
Bayside building at Virginia Beach, and it's
yeah.
the same building as the library, if I remember correctly, at the Chesapeake campus.
Okay, yeah, okay. Thank you.
All right, no problem. And that's Jonathan, right? Jonathan Gray.
Yeah,
Gotcha.
Jonathan, yeah. All right.
All right, have a good one, man.
Have a good one.
Bruce, do you have a question, sir?
Yes, I took the test, the
Uh-huh.
quiz, and it said I got all the questions right, but it also said a 55 out of 100.
55, not 95.
Yeah.
Okay, that's weird. I had another student tell me it got 95 out of 100. They got them all right. That means something's messing up with the online test. So I got to check that out and figure out what that was. I will do what I can to figure that out. If I don't change it, if I forget to change it, let me know like next week. But I'll definitely look into that probably tonight. But it's if you got them all right, that's all I can do. So I'm going to give you 100 no matter what.
Okay.
Okay. But it's clearly something messing up with the online test, so I got to go check that out.
All right.
All right.
Thank you.
Thanks, Bruce. Have a good one.
You too.
Bye bye.
Bye.